welcome everybody. All right then, so welcome everybody. We are going to discuss how we can report errors in different modes so that we can enable flexible recovery patterns that go beyond what we have been working on in the past few years about in ULFM. So this is an extension or a revamp of the ULFM reporting modes so that we can handle more diverse recovery patterns. All right, so for those that have not been on board with the program, so this is a background about what ULFM does. So basically the idea is that we are going to operate across failures, and the way we are doing that is that if there is a failure, the MPI operations are going to report errors, and these errors in turn can be circumscribed to a set of processes that are interested in knowing about that error. And you will be able, as an MPI programmer, to call operations to continue communicating between the non-fail processes if that's what you want to do, or to call different new operations that we add so that you can restore the capability of doing collective operations in a shrink mode, or you can restore the capability of communicating among the same number of processes that you had before. So basically, we have three levels, three operations that we are going to do in order to achieve this goal. We do the failure notification. So basically, your MPI operations are going to report errors if they cannot fulfill their specification because the process failure interrupted them. And we will have some way of propagating the fact that there was a failure so that you can interrupt the communication pattern that is ongoing globally, or at least not globally, but on the communication, on the communicator that you are using. And then we provide the facilities to restore communication capabilities. All right, so far so good. The goal is that we can tolerate failures for non-malleable applications, malleable applications, run-through applications, all sorts of applications. All right. So we have an implementation for that. The performance is pretty good. So these graphs here are showing the performance distribution of, in blue, OpenMPI without fault tolerance, in orange, OpenMPI with fault tolerance. As you can see, the latency is almost the same with and without fault tolerance. The distribution is very similar. Same story for bandwidth, and then we also have the same sort of graphs for collective operations, all sorts of stuff, and this is the same story all across the board. The performance is very minimally impacted, if any difference. We have a number of papers that describes how we do the fault-tolerant operations, so you can refer to that if you are interested in how this is made. All right, so we have implementation, and this is available for users to play with. Sorry, I went too fast. So yes, so this is available for the users to play with, which they did. And so we have basically three types of users that have been, so there is a lot of exploratory work that has been using this to do some sort of fault tolerance. We can group them basically in three different groups. So the one group is application-based fault tolerance, in which you can do run-through failure mitigation. So for example, this is the example that we have here on the bottom left. You have domain decomposition PDE, which are very amenable to do recovery in domains, in subdomains, and on the master worker type of application workload that are also very amenable to do run-through failure mitigation. Then we have the let's say global recovery strategies. So here we have two different types of global recovery strategies. On the left, the Phoenix framework, which is doing well, on that particular version was doing global checkpoint restart at the user level. So the framework provides all the infrastructure for the application to do the checkpoint restart. And the framework itself does not expose ULFM, but it uses ULFM internally to provide the facility. And then in the center, we have the database application, which is using ULFM to do what basically they were doing with sockets before, but they are doing basically the reliable commits to the database using the ULFM construct so that they make sure that if a failure occurs, they don't commit half transactions. And then we have non-HPC or HPC, but not directly global recovery strategies. So typically, MapReduce application can be implemented on top of ULFM. Also, programming languages can use ULFM internally to provide facilities. Like in the Extend language, you have a local recovery strategy that is implemented in the language. And so you have the concept of a failed place. When a failed place error is reported by the language, you just interrupt that particular process has been interrupted. The rest of them, they don't have to be interrupted. So that's also based on top of ULFM. So, okay, so that has been a good run, but we found when we were working on this that there are some limitations to what we can do or inconvenient usage patterns, and that's what we are trying to achieve here, is to fix this. So we see that we found three different places where we want to be reworking the way errors are reported. So the first step of that process of recovery is reporting errors, and we want to change how errors are reported here. And so the first step is to identify what is the scope on which errors should be reported, and then how many or during which operation errors should be reported when they are reported, and if errors should be reported only during operations or otherwise. Okay, so the ULFM model that we proposed before, or the keep it local model, as I call it here, is basically taking the premise that we are going to interrupt only operations that are directly impacted by the failure. So if a process is doing communication with a failed process, then that operation is going to report an error. Otherwise, it should not report an error. So the reason why this model is interesting is because in many applications that are doing run-through recovery, so if you have, let's say, a master worker type of application, or a mendable stencil, or some other sort of application that can continue doing point-to-point between the processes that have not failed, there is really no reason to impact the application and cause the application to pay some cost for recovery, because it doesn't care. It can just continue operating between the non-failed processes. So that's why this model is interesting, and it provides the basic functionality. In some sense, it is going to the crux of the MPI semantic. You interrupt only the operations that do not provide the semantic that you expected. Okay. So of course, not all applications can deal with that sort of model. So maybe you have an application that needs to do some global recovery pattern. So the way we dealt with it in ULFM is to provide explicit propagation. So in the explicit propagation model, when the process here, the process P1, has an operation that gets interrupted by a failure, if P1 was supposed to be communicating with P2, P3, like it does here in that communication pattern that has transitive dependencies between the processes, P1 can decide to explicitly call the MPI come revoke operation to interrupt that communication pattern that is ongoing. So given that facility, we can now join all the processes that need to join the recovery procedure can be interrupted and join into the recovery procedure without being stuck in their own interrupted communication pattern. Okay, so that's working, but we have a problem if we look at a more complicated example in which the application is separated in different software modules which do not share global variables. So imagine that you have an application that is using different libraries, and this library both have their duplicate of the main communicator of the application. And they store that communicator into their own local variables that they do not share with the other libraries. So the explicit propagation, in order to be able to trigger the explicit propagation, you need to be able to access the communicator that the library is using. So that means that library 1 cannot, if they do not share global variables, the library 1 cannot interrupt the communication pattern of library 2. So it's good enough in the first use case here, temporal SPMD composition. The library 1 is executed, then the library 2. Okay, good. Then we don't really need to be able to trigger the recovery of library 2 from library 1. But in the other nodes, if you have domain decomposition or nesting of libraries, it is very possible that you need to be able to interrupt multiple libraries at the same time. So the solution we propose is to be able to control the scope of error reporting. And we want to retain the ability to do the local reporting that we were doing before, because it is a useful use case for some applications. But we also want to be able to have components that can trigger the recovery, even when implicitly, even when they do not know, even when the error might have happened in another library that is not currently executing on the process. So the way we achieve that is that we will set on the communicator of the application the error reporting mode. And so we have three different reporting modes. The first one is local. So the reporting mode local means that your errors are pertaining only to your current operations, and they do not pertain to anything else. So this is what I was describing originally as the ULFN mode. But you can also set your communicator to report all errors that have happened in the group of the communicator. So if your library wants to be able to recover every time there is an error in the group, even if the operation currently ongoing is not an operation that spans on the entire group, you set that mode and you will get an error for every failure that happened in the group of the process, in the group of the communicator. And then you can set it to global, in which case you will get a failure for every an error for every process that fails anywhere on the universe. So a little example to explicit what's going on here. So in that little example, we are splitting the MPICOM world in two. All the odd processes go into a subcommunicator, and all the even processes go into another subcommunicator. And for all purpose, we will consider that these communicators are disjoint, and you cannot revoke them from one to the other. They are disjoint actually, and you cannot revoke one from the other. So here we are doing we are creating an info object, and we set the special info MPI error scope to group, and we set that info on the communicator. So that means that after we've done that, this MPI send receive pattern, which is basically doing the communication pattern, and we see in the previous figure. Let me go back a little bit to show that again. So you see on this communication pattern here, we are transmitting a token, and this repeats. Okay, so this is that send receive you're receiving from your predecessor, you're sending to your successor. All right, so by default, the send receive would return an error only if one of your right or your left neighbor has failed. Because we have set the info error scope to group, then it means that any error anywhere in the group will automatically produce an error during the send receive. The thing to note here is that because we have set it to group, it's still applying only for errors in the group. So the errors that are happening on odd processes will interrupt operations that are running on the odd communicator, and vice versa. On the right example, we are doing basically the same initially. We split the communicator into in odd and even processes again. But then one of the processes, one of the communicator, we set the error scope to be the group, like we did before. But on the second one, we set the error scope to be the global. So that means that now, on the hot processes, only the failures at other hot processes raise an error when we are using the communicator. However, because we've set the error scope to global, on even processes, a failure at any process raises an error, even the failure that happens on the hot processes. Any questions on that? All right, so I keep going. So one of the rationale, beside the fact that we wanted to support the master worker on the run-through stabilization failure day modes in applications that can support this mode, one of the rationale for selecting the local scope as the default was that we were afraid that there would be dire consequences for mandating that we have a global failure reporting. And so we have, here are the results that are coming from multiple papers that we presented about failure detection. And basically what we see in these graphs, you can see here the gray area is the normal variability of results without fault tolerance. On the x-axis, we are increasing the stress that is caused by the failure detector by setting the timeout to be increasingly short. So, and as you can see, for reasonable timeouts for failure detection, the overhead that is caused by doing global failure detection is very reasonable and is basically still within the noise of the normal execution. So the takeaway message here is that actually the cost of doing group on global detection is not that expensive. So there is no real reason not to be able to provide this functionality to the end users. They are not shooting themselves in the foot by setting it on. All right, so the next topic is error uniformity. So what is the problem with error uniformity? So here I have a little example code that is doing a bunch of MPI broadcasts in a loop. And before I enter that little code, I have set an error handler, which will be triggered every time there is an error, and will go into a recovery procedure. So the problem that, so this code is incorrect, and the problem with this code is that, is illustrated by the figure on the right here. The broadcast is operating over a propagation topology internally. So that's how the broadcast is implemented. And what that means that some of the processes will, if there is a failure at rank 2, all the processes that are not in the branch of rank 2 will complete the broadcast. They will receive their messages as expected. And if there is no, it is very possible that all of that happens so quickly that even if we have failure propagation, this completes before we propagate the failure. So that means that for the processes that are on the one branch, they will all complete successfully. For the processes that are on the two branch, well, they cannot receive the message. They were supposed to receive it from the dead process. So they cannot receive the message, so they will have to raise an error. And so this is what we call non-uniform error reporting. The broadcast has returned an error at some processes, but not at some others. So now the problem with that is that some of these processes are not going to go into that error handler, the processes that could not finish. They will go into that error handler, while the rest of the process, they will post another broadcast. And that other broadcast might be deadlocking because it's waiting on processes to participate that are not participating like they should. So they are not matching their operations, or no, the code is incorrect. So of course you can fix that. You can add an MPI come revoke, and that will make sure that everybody is interrupted in the next broadcast, and so they will join into the recovery procedure, and that will work just fine. All right. So now I can complexify a little bit my example to still make it problematic. Consider an SPMD application that is bulk synchronous or that has an iteration count, and it is very important for the recovery procedure that I restart that all my processes enter the recovery procedure at the same iteration. Just imagine that you are modifying the data set every time you do an iteration, and if the iterations are not the same when you're recovering, you get wrong results. This is the use case that's actually found in the wild, so this is pretty important. And the problem here is that, okay, the errors are non-uniform, so we are going to interrupt that all reduce. Everybody is going to interrupt that all reduce eventually, but they will not do it at the same all reduce. So they will interrupt it at the next all reduce, possibly, if they do it when they reach that revoke here during the error handler. And so that means that we have a miscounting problem here. The iteration is not the same at every rank, and the result is possibly incorrect. So again, we have a solution for that, but the solution is pretty unpalatable because the solution implies that after every time we do an all reduce, we are going to verify that the all reduce was successful explicitly, and we have to insert that code everywhere in the application code. So you basically you cannot do that during the error handler. You have to do it as the return code of the operation, and that is going to pollute your entire code base with this error checking. So a better solution, or the solution that we propose here, is to be able to control error uniformity, again, on a per communicator basis. And so when you create, or when you have a communicator, you will be able to set, as the user, if you want your errors to be non-uniform, but you want your errors to be uniform, and that means that all your collective operations are going to return the same error code if there is any error during one of them, or success at all rounds. And then we have a specific mode that is intermediate to local on collective, which is for create operation. You want that that same behavior, but only for communication, for operation that create new communicators, not for all collective operations. So why do we want to have an intermediate mode for the communicator creation operation? Well, the reason is that having an error during an MPI communicator creation operation is severe. You might end up with the resultant communicator that has been created in an inconsistent state. And so, because the consequence of using that communicator without checking it is very severe, generally you never want to do it. And in some of the intercommunicator operations, validating that the communicator is correct is difficult. So here having a mode in which this is done automatically is very useful because it really simplifies users' code. Okay, so a little example again to understand what we are talking about. On the left, we have the non-uniform example. So basically, you are operating on a communicator. You set the error handler MPI errors return because that's the only thing you can do if you want to do uniformity yourself. And we do this. We do repeatedly the iterations in which we do computation, communication, computation, communication. And every time we do a collective communication, we have to verify that the collective communication has succeeded. And so we have to add this code every time we do one of these communication phases here. So that's pretty irritating. So in the uniform example, we still operate on the communicator, and we set on that communicator that we want our errors to be uniform for all collective operations. And now the user code is much simplified. So we have a normal MPI code, and the error handler are going to be triggered correctly and in unison at all the MPI processes without polluting the entire code base. So it's pretty neat. Yeah, so that's all I have to say about that. So why don't we say that we always want the errors to be uniform? It is the easiest thing to do for the end users. For the end user, it is obviously a lot easier to deal with. However, there is a severe performance penalty. Well, there is a severe performance penalty on latency, at least. As we see on this graph here, so we have the all reduce on the broadcast, the normal version on the uniform version of them. And as you can see, for the broadcast, the latency is multiplied by a little over 4, and for all reduce, the latency is doubled, more or less. And then if you go for larger message sizes, you get some amortization going on because you do not have to pay, because the cost of making sure that everybody returns the same error code gets amortized over the cost of the operation itself. But as you can see, for an application that would be exchanging a lot of small messages with collective operation, the cost can be pretty severe. So we want to be able to turn this on and off on demand. So another interesting aspect is that because we can turn it off and on per communicator, the application may use some communicator on which this optimization, in which this feature is set, on some other communicators in which this feature is not set. So it can have uniform operation when it matters, and high performance operation when it matters.
So why is this impact of performance? Why do we have this? I don't understand.
So what happens is that when you're doing the operation, you're doing the broadcast operation, let's say, you cannot, the operation is a one-to-all operation, so, but the result of returning the same error code is an all-to-all operation. And not only is it all-to-all, but also it's an all-to-all and fault tolerant. So basically what happens is that you're doing a broadcast for achieving the semantic of the call, but you have to do an agreement inside the broadcast to achieve the semantic of the error returning.
Right, which I don't need, right? Because I only want to know, so the alive processes only want to know about the failed processes when you have a failure.
Well, but you don't know if there is a failure or not, and you have to verify every time. So that's the problem here.
Right. I mean, this model is assuming you verify it every time, but we could have other models where you don't assume that, and you only communicate the failure when you see the failure.
That's right.
And you still have a uniform. So there is a possibility of a different model here, you know, in addition to the ones that you have presented, where I don't check every time, but if one of the processes detect a failure, you can still uniformly later propagate this failure information to everyone.
So, all right. So what you are referring to is what you are referring to is the scope of the reporting. So uniformity is an operation property. So the collective operation will return an error code at all ranks or not at all ranks. What you are referring to is that my processes will receive an error no or later, but they will receive an error or they will not receive an error. And this was the first property. The scope property is giving you that control. So if you set the scope to be the group, then even if the operation did not return an error now, eventually you will get an error because there was an error in the group. Okay. Do you see the difference here?
I guess then I don't understand why do we need this. If we can set the first one, where if I have an error, everyone will receive it, I don't understand why do we need this one.
The first one is setting the span on which the error is reported. It doesn't set the when the error is reported. It's a location, if you want.
Okay.
It tells you that it tells you which ranks you are looking for when you are looking for errors, looking for failures. The second one is telling you when these errors are going to be reported. And you know that these errors are going to be reported at the same time.
Okay, and so for the second one, we have, so how many options we have for the second one? We have at the same time, which is this case, right?
Which is uniform, and we have local, which is not at the same time. And then we have at the same time, but only for creation operations. So let me go back a little bit.
What is the local?
So local means that if you do a broadcast, you might return an error or not an error at different ranks. So the same broadcast operation, the same broadcast communication, will return an error at some rank, but not at some other.
Right. Mm-hmm.
In the collective mode, all the errors are uniform. So that broadcast will return an error at every rank.
Mm-hmm.
And the create mode is the same, but only for MPI-COM dub, say, or MPI-COM split.
Okay. I guess I don't understand what is the problem with not reporting the error at every call. Because for a bolt synchronous application, the pattern that I would have is I have a main loop and I have in that main loop, I have a bunch of MPI calls in which I could have a failure. But then typically at the end of the loop, I have a synchronization point where I checkpoint the state of the application.
That's right.
And I can simply, at that point, detect the error or get the final error number that I get. And even when I have failures in the middle of the loop, that's still fine because I will detect it at the end.
So that's right. So you are exactly describing what we are talking about here in the local error reporting. So you would set your error reporting to be local.
Right.
Because you do not care for the inside of the iteration, and you do not want to pay the performance penalty we were discussing just a second ago.
Mm-hmm.
And then for that last operation that is committing your checkpoint, you would either use an explicit agreement or you would do that operation on a separate communicator on which you have set the collective uniformity.
Mm-hmm.
So that you know that this operation.
Right. So that's that's the use case I think probably a large number of large-scale applications would use.
Mm-hmm.
I guess I'm trying to understand why do we need, or what application will use the other one that has the high overhead, right?
Well, the high overhead is the one where you're committing your checkpoints, let's say. If you're doing an all reduce to commit your checkpoint, you want to make sure that this checkpoint is committed successfully by everybody. So that particular operation, you do care that it is performed properly. Or not. Not everybody agrees on that. So that's what this mode gives you.
All reduce for checkpoint. Yeah, I don't understand that, but I don't see how why do I need an all reduce for checkpoint? This is like this is application checkpoint, right?
That's right, but then you need to know if the checkpoint is successful or not usually. So maybe you want to erase the previous checkpoint. I mean, there is a number of cases where that happens in the application. So I was talking initially, if you remember, about that SAP database application.
Mm-hmm.
And basically, what they do is that they are doing a set of all reduce on the broadcast to commit to do the commits on the database.
Mm-hmm.
And they really care that the commit is completely successful or completely failed, not something in between. So for them, it is very important that the errors are uniform. So that's one use case. You can see here that this is one use case where it is very important that all your operations are uniform.
So they only have all reduce basically. This is a simple application that is only using all reduce.
I don't remember exactly the details, but I believe they have broadcast also. But yeah, it doesn't really matter what type of collective operations. What matters here is that they care that they fail in unison.
Okay.
Okay. Any other questions on this, or we move forward? All right, so the last topic on error reporting is error synchrony. And here we are more talking about an idea than a concrete proposal. Well, maybe it is a concrete proposal, there is enough material here to be so, but it's a tentative idea, so I'm really willing for getting some comments about it. The basic premise of the proposition is that imagine that you have an application that is doing some sort of communication pattern. We get an error, and we are going to report errors only during MPI operations. And so if it happens that we have one of our processes, like the one at the bottom of that synchronous error reporting case here, that computes for a very long time, that process is going to compute, and it will take a very long time before the error handler is triggered at that process, and it can join the recovery procedure. And because of that, all the other processes are basically wasting time waiting for that process to get interrupted and join the recovery procedure. So maybe a better option is to be able to interrupt that process while it is computing so that it gets quicker into the recovery procedure and we don't waste all that time waiting. So that's what the proposal is trying to achieve here, is trying to basically enable the triggering of error handlers outside of MPI operations. All right, so the way you set that again is by setting an info key on the communicator, and you will set an info key that says either the errors are reported only during operations, so that's the default mode. So basically, you will get an error when you are doing an MPI receive, an MPI wait, or something usual. Or you can set the MPI error mode to be asynchronous, in which case the error handler for your communicator may be triggered at any moment. So whether you're doing MPI receive, MPI wait, or you are doing some sort of computation, if the implementation supports it, the error handler might be triggered when you're doing something else. So of course, the fact that you're triggering the error handler while you are not performing MPI may mean that you have to have some sort of asynchronous progress engine in the MPI implementation, and we generally do not want to make that mandatory. And so what we did, what we propose here is that this is a preference that the implementation says. I prefer my errors to be possibly asynchronous, but the application has to still be correct if the errors are not asynchronous. And the MPI implementation does not have to do any sort of error reporting outside of MPI operations. It may do so if the flag is set, but it doesn't have to. Again, this is set on a per communicator basis, so some of your libraries or your operations that you are doing may not benefit from that asynchronous mode, or may not be prepared for dealing with that asynchronous mode in which error handlers are triggering at any place. So for these libraries or operations, you would use a communicator on which you do not set that mode. And for when that makes sense, you would set that mode on a different communicator, having a fine-grained control about what's happening with your error handling. Okay. Yes. So one thing that needs to be noted, I'm going back one slide here, but one thing that needs to be noted, because the error handling happens outside of an MPI operation, you do not all the communicators for which that error needs to be triggered. So you might have more than one communicator that is set in the asynchronous mode, and for which the group scope matches. So in this case, you might have to trigger the multiple error handlers one after the other when an error is asynchronous, or not just the one that is attached to the communicator that is pertaining to the operation that you are currently doing, because it's happening outside of an operation. Okay, so the last thing I want to discuss about this particular topic here is we are using MPI info to control the way the communicators, windows or files are behaving. And we are using this we are using or maybe abusing the MPI info for that purpose. So the traditional way info are used in MPI are as assertions to optimize. That means that the MPI program may express to the MPI library that it will refrain from doing some sort of communication pattern or using some sort of feature, like it will never use MPI any source or something like that. And given that assertion from the MPI program, the implementation may be able to optimize with the knowledge that the optimization will not cause a difference in observable semantic as long as the application abides by the assertion it has said it was going to. So basically, or said otherwise, the info key does not change the semantic of the MPI operations. It just it just tells the implementation that some semantics do not have to be respected because they will not be visible because the application is not going to use them. Here, this is not what we are doing. We are doing something slightly different in what we are mandating different behavior based on these info keys. And the API application is then expecting to see different behaviors from the interfaces. So this is not illegal in the strong sense, but this seems to be contrarian to the intent that was defined for the info object in the info object chapter introduction and in the communicant for info subsection that describes what are info assertions. So an alternative way to set these preferences on or to set this reporting mode on the communicator might be to use an explicit interface that sets these modes not with info but with, let's say, an enumerated list of constants that you can set on the communicator's window file. So that's what we have here, MPI set error reporting, and then we can set the 3 features that we were discussing before with the different constant that represents the modes in which we can operate. So is there, before we move on to the slightly different topic, is there any more questions about that, comments about how this is going? Do we like this?
So why do we have to use info? I mean, can we just propose a different set of codes?
So that's what we are discussing here, yes. We don't have to use info. I did that because it was, actually because when I was doing the implementation, that was very convenient. But then at the last meeting in Chattanooga, the issue of info was discussed again, and again it was thrown upon by the forum. So given that the feeling of the room was not very hot towards having info that are controlling stuff, I think, as you said, that we need to have interfaces. So the interfaces that we are proposing here, yes. So yes, if we have interfaces, they could take the form that the 2 last lines in that slide. The set error reporting is not taking an info as input; it's taking a set of enumerated constants.
Yeah, I think this is cleaner, in my opinion.
Okay. So anybody objects to moving towards the interface mode? So glaring silence means approval. Okay. So I think I will write the text accordingly to that last 2 pieces of material. Any other questions or comments on the modes?
So I have a question regarding the detection. I think that's the first part of the presentation. You were talking about failure detection, right?
Mm-hmm. Yeah.
So what kind of failure detection are we talking about here? Is this a kind of like an agreement or consensus kind of detection that the implementation would perform?
All right, so let me get
or
the material that will explicit this. Okay.
So maybe, yeah, I don't remember what slide was, but I mean, at some point you said you talked about detection.
Yeah. So basically the detection modes are pertaining to what operations are going to be interrupted when there is a failure. So the default mode is to interrupt only the operation in which you cannot fulfill the semantic. So here in that example, you've got P2. All right, P2 is in a receive from P1.
Mm-hmm.
So because P1 has failed, that receive cannot fulfill its semantic anymore because I cannot provide the message in the buffer because P1 did not provide it. So I have to report an error at P2. There is no choice here. That's something that I have no choice about.
Mm-hmm.
Now what happens for P3 is that P3 is receiving a message from P2, and P2 is live, and so in theory, I could receive the message from P2 later, and that should be able to work, right?
Right.
Yeah. So in the local reporting mode, I will not interrupt that operation automatically. So
which operation?
The receive from P3. I would not interrupt that receive from P3 under the assumption that P2 is going to post the send that matches and everything is going to work fine.
Well, how? Because P2 cannot proceed until it receives from P1, right?
That's right. And so that's why we have two different modes from then on. So you're getting exactly to the crux of the issue here. Either P2 is going to do whatever it was doing before, and we continue as a run-through recovery, so we do not change the communication pattern and we continue with whatever processes we have, or P2 has to interrupt P3 because it's not going to match that send it was going to do originally. So we have then two ways of doing it. One is to do the explicit recovery, interruption, and we call the MPICOM revoke operation, and that's doing explicit propagation of the error. So P2 has found that P1 has failed, and it will call revoke to explicitly propagate that error.
Mm-hmm.
Or we set the mode to either group or global. Well, we set the error to group. Let's keep it simple now. We set the error to group, and that means that all the errors are going to be implicitly reported. So it is as if P2 had done the revoke, but the revoke is done internally by the implementation. So eventually, all of the received everywhere are going to report an error.
Okay. Yeah, I mean, in the majority of the both synchronous codes, once you have an error in one of the processes, the other ones will not be able to make much progress. So
that's right. So that's why we add this feature to have it automatic, so that you don't have to bother with it explicitly, and then we can also do it outside of the scope of the communicator. Okay. You can observe failure that happen at other processes, even if you're not operating on the same communicator or in the same group of processes. So that's what the addition that we have with these new modes here. Mm-hmm. Local, group, and global. So local is you interrupt only the operation that you have to interrupt. Group, you interrupt all operations that are on a communicator that spans on the failed processes. On global, you interrupt all operations on that communicator if a failure happened anywhere. Right.
Okay. Yeah. So the last one is essentially the global well, it supports the global restart model that.
Yeah, that would be the trigger for a Renit type of.
For Phoenix or Renit type of, yeah.
Yeah, and I just want to make sure. So in this error mode, error scope assumes still MPI runtime is doing has a some correct guarantees certain correctness in its internals.
Yeah, that's so. In these two mode, group and global, you have some sort of background propagation of failure going on, and that happens automatically without you doing anything except setting the mode.
Okay.
Yeah, so that's kind of like what Phoenix and Renit does essentially, automatic cleanup of the state, right?
Yes. Yeah. Even though it does some some work inside, but
right, there must be some communication inside to everyone, at least in the last one, the global, where everyone will receive the error. And this is what will allow us to move back to the previous checkpoint in the main loop. Yeah, I think that would work. So the other thing is, okay, so how is the failure detected? Aurelian. So I guess you do. Are you using timeouts or
So
how?
that's an implementation detail that does not have to percolate up to the interface, but in practice, in the implementation, we use some heartbeat on timeouts, yes. And
Oh,
so
no, but I thought you mentioned that, right? In the presentation, you talk about timeouts.
yes,
That's what I'm asking.
So in the I mentioned it because there are multiple ways you can do a failure detector.
Right.
Some of them we are using, so this is what we have on the SWIM failure detector here.
Right.
The SWIM failure detector is doing basically a randomized probing of the processes. So it's sending heartbeats to processes randomly and waiting for an answer. And if it doesn't get an answer in some amount of time, it will consider that this process is dead. But because it is randomized, the timeout for detection is pretty long, and the noise is generating is pretty high. So you send actually a lot of messages to a lot of processes to probe them randomly, and sometimes you create hotspots, sending many timeouts, many heartbeats to the same processes. So this is rife with problems. And this was the state of the art before we worked on failure detection a couple of years ago.
Right.
And
I mean, I understand this is an implementation issue, but
yeah.
That doesn't mean we don't have to discuss these issues. We need to discuss these issues.
That's right.
This affects the actual results that we're going to have.
And so that's why we are happy to report that with the proper algorithmic methodologies, we can have something that has a fixed degree of observation, deterministic behavior, and shorter detection time than what was the state of the art for.
I mean, we do have a very different approach for the global restart model that we've been working on, where we don't do this time and stuff. We just rely on the runtime, the resource manager, to tell us when a process fails. And that's
that's right. That's another implementation of the same thing. And probably the runtime itself is doing some sort of heartbeating internally that you don't see, but that's just the same.
For node failures, yes. For process failures, no.
Okay.
Yeah. So it depends on the kind of failure. If you're doing, so if you talk about, for example, Slurm, for process failures, it will not do any heartbeat.
Yes.
Yep.
The same of MPI, we detect process failures by seed child, basically. And so that's instantaneous.
Yeah. It depends on the kind of failure.
Yeah. And also, Ignacio, do you also envision any development of Flux?
Yes, we're working on Flux as well to provide this kind of stuff.
Yes, because I think I guess the Flux is also maybe you also envision how MPI session will coordinate with Flux new capability for maybe dynamic resource allocation, etc.
Right.
Yeah. And by the way, so at this moment, it is okay for me for the failure detection, also the recovery capability. And recently, I'm also very, very worried with fade slow type failure. I mean, not fail stop. Fail stop. I mean, fail stop is basically something is wrong, maybe underlying operating system or middleware just kill a process or shut down the node. But we are actually, in Sandia and especially Trinity system in Sandia and Los Alamos, we have been observing fail slow type failure. Basically, something is wrong with the system, or maybe software, could be software, hardware that triggers massive slowdown of a particular process or particular node. And I still want to know how ULFM can deal with this. Maybe resource allocation, resource manager can report something to ULFM. This is my hope.
ULFM can actually, yes, ULFM could help with that in the sense that it will not detect. It will detect some of these failure as process failure, because if you're slow enough, you will act as if you were dead. Mm-hmm. But if you're just in between these two states, you're slow but not quite slow enough to be dead. Another mechanism could be used to detect that there is some slow process going on, and that process could be aborted, and then trigger a process failure as normal.
Yes. Yeah. In fact, we have there's a couple of major incidents in Trinity is slowdown of a node. I think, sorry, it happened actually 25x slowdown, and MPI still treated it as a normal program, and the program entire applications, got slowed down by 25x. So, yeah, just FYI.
Mhm. Yeah, that's an interesting issue indeed. Yeah.
So Aurelian, we're at the top of the hour, so we probably
Yes,
need
we
to
are.
wrap this up.
So, all right. So this is what we are proposing, and we will have text ready for June. So let me get back to the conclusion slide. I had some other material, but we'll discuss that during the working group, I guess.
You mean May? When is the meeting? Is it in June or May?
Yeah, it's last week of May. It's usually in June. So.
Okay.
All right. All right. So this is what we have here. So basically, this text the text that accompanies these ideas should be ready in June. I am pretty confident it will. And then we will be able to present this and get a full comment on the text by then. I encourage people to read the text before the reading so that we can capture any sort of problems before we get there, so that we can match the deadlines if we want this to be going forward for the next version of MPI. Or at least be able to decide on it before then and not get caught by the clock. That would be great if people could comment on the text before we do the reading. The other thing that might be ready by then is the revamp of MPI COM Failure Act and COM Failures Get Act. We did not discuss that today, but we are also thinking about it and working on it. And so eventually, possibly, this will also be ready by June. And with these features, we get basically support for master worker on Monte Carlo recovery. We don't get full SPMD recovery yet, but we do get master worker on the Monte Carlo type of workload. So that's already something. All right, that's all, folks.
All right, so next week we have a 2-hour session. So the first hour will be, I think, Ryan Grant presenting Pine Points, and the second hour will be people. I assume Jeff Squires and Tony talking about the function pointer interface. So we'll see you then. Thanks, folks.
Thank you, Aurelian, and everyone.